Okay, welcome back. In this video, we'll think about kin selection and what it is and how Hamilton's rule explains it. So let me get to my PowerPoint slide. Excuse me. I think we were here. Okay, we just went through some examples of how to calculate relatedness or coefficient of relationships or coefficient of relation. Okay. Now we're starting to think about how could cooperation evolve as a result of kinship or kin selection. Kin selection says that natural selection in favor of behavior by individuals that may decrease their chance of survival but increase that of their kin. Kin selection is essentially selection for what we might call self-sacrificial behavior that benefits the genetic fitness of their relatives. Cooperative behavior, in which you are foregoing your own reproduction to help your siblings raise their offspring, would be an example of behavior that might be selected for if you have a large, if helping your relatives really helps them. Or another example might be if an animal makes alarm calls when a predator is near. That might be a self-sacrificing behavior. I mean, the predator will see the alarm caller and likely pinpoint it and maybe kill it. It might be self-sacrificing to make your alarm call, but it might benefit all of your relatives that you live with and protect them. And so it might be selected for. Cooperative behavior might be selected for because of this kin selection. All right? Hamilton came up with a rule that explains how altruism could have evolved with math, basically. All right? And here's what Hamilton said. Hamilton said an allele would be like a genetic a version of a gene, right? An allele associated with some trait, some cooperative behavior like alarm calling or helping at the nest, cooperative breeding, something like that. An allele associated with a cooperative trait being studied will increase in frequency, will be selected for whenever, and here's our let's just make sure I'm ready to go here. Here's our relationship. Here's our math. Whenever this is true, the sum from 1 to A, where A would represent the total number of relatives, of R times B minus C has to be greater than 0. What on earth does this mean? R times B minus C. Okay, so Hamilton says cooperative behavior associated with having a particular gene will increase in frequency, will be selected for when this is true. So what does this all mean? Well, let's look at what each part means. R represents the relatedness, the value that we just could calculate. We just made some calculations for in the last video. B represents the benefit to that relative. So R times B would represent the benefit to a relative times how closely they are related to you, minus the cost of the cost associated with the helper who's doing the job of cooperating. How much is it going to cost that individual? So let's go back and think about this. Hamilton says that a cooperative behavior should evolve when the benefit to relatives for doing this behavior is greater than the cost to the individual doing it. Sometimes we even write it like this: R times B is greater than C. That's really the easiest. That's how I like to think of it. Oops, R times B is greater than C. The benefit to the relatives, and that includes all the relatives that benefit from your behavior, is greater than the cost to the helper. So it might be worth it to call out that alarm call, risking your life. There could be a cost, a big cost, but benefiting the 25 relatives that you live with. That might evolve. Genes associated with that cooperative behavior would be selected for over time. That's what Hamilton says. That's what kin selection is. Selection for traits that may harm an individual. An individual may cost an individual, but will benefit that individual's relatives. Now let me ask you a few of these questions down here to see if we understand this relationship. When should selection favor kin helping one another? When should selection favor cooperative behavior among kin, among relatives? When R is high or low. So R is the relatedness. When R is high, you have close relatedness to the helper. Well, then this value is going to be bigger. R times B will be bigger, right? That's going to favor kin selection. So I'm going to say R has to be high. If you have a high, or if R is high, then we'd have perhaps selection for this cooperative behavior. What about B is high or low? B is the benefit that each relative is going to gain from your cooperative behavior. Well, kin selection is going to favor cooperation when the benefit is high. You're saving their life, or you're providing them with food, or you're protecting them from predators, and these are big benefits, right? What about the next one? When C is high or low relative to R times B? Well, C is the cost to the individual. When C is low, scrub jays, for example, stay and help their parents raise young. And that's at the cost of reproducing themselves. But the cost is pretty low because most 2- and 3-year-old scrub jays that help out at the nest, they don't even get a territory. They can't even get a territory. They can't breed. So the cost for them of helping is really pretty low because they're probably not going to breed anyway. They're probably not going to have their own offspring yet anyway. All right, how about this? When should selection favor kin helping one another? When A is small or large? A is the total number of relatives. Well, the more relatives you have that you're helping, the better off the more likely this trait is going to be selected for. So I would say when A is large, right? When A is large. Let's take a look at some examples. Here's one situation that is pretty interesting. Belding's ground squirrels live in large, complex societies. In these societies, females stay in their natal land. In other words, females stay where they were born. Males leave their natal land and find a new population to go to. Okay, so females have many, many relatives in the colony, but males don't. Now, what researchers noticed was females seem to emit a lot more alarm calls than males. Why is that? Okay. Well, first of all, and also, why would a Belding's ground squirrel? Apparently, they make alarm calls. When they see a fox or a snake or a hawk, they emit alarm calls, and that alerts all the members of the population, and they hide in their little holes and whatnot, right? So why would they do that, and why do females emit more alarm calls? Well, this kin selection would say, hey, maybe they make alarm calls because R times B is greater than C, right? The benefit to their relatives, especially if they have a lot of relatives in the community, is going to be bigger than their potential cost, which is perhaps getting eaten, but maybe not. And why do females emit more alarm calls than males? And is that really true? Researchers have shown that that really is true. Females emit more alarm calls than expected. And so this graph down here at the bottom kind of explains or kind of shows that. Oops, I'm struggling here. So down here at the bottom it says how many alarm calls are these animals expected to give based on the population size versus how many they actually observed. So the green versus the orange, they should be similar in size, these bars. And it turns out that females, 1-year-old females and particularly adult females, emit way more alarm calls than they're expected to. Adult males emit fewer alarm calls than they are expected to. And then these juveniles don't emit much. What's happening here? This is exactly what Hamilton's kin selection theory would predict, right? Because females have a lot of relatives in this population. Males have very few genetic relatives. They have their offspring, right? They do have some, but they don't have their cousins or their sisters or they don't have siblings. They don't have cousins around. They just have their offspring if they've successfully bred. Adult females, on the other hand, have a lot to lose. They have a lot of relatives in the community. You got cousins and second cousins and nieces and nephews and your own offspring. They're much more likely to emit alarm calls because R times B is greater than C, right? That's the idea, at least. Well, how do you determine that R times B is greater than C? How do you really calculate B and C? How do you calculate the benefit of helping to your relatives and the cost of not helping? That's a really tough question. Researchers came up with kind of a shortcut. It's called the offspring rule, kind of a sneaky way to calculate benefits and costs, or a simpler way to apply Hamilton's kind of complex rule. Brown et al. Studied this in the 1980s, and they said, let's think about simply the number of offspring that are born and survive to get a handle on costs and benefits. So we could say the number of offspring that survive at a nest, the number of offspring that don't survive, the number of offspring that this individual produces, the number of offspring that its relatives produces, those kinds of things. Just go by offspring that are born and survive. Okay, so here's what Brown studied. Brown studied these birds called gray-crowned babblers. I'm not even sure where they're from. I really don't know. Not in America. Now, it turns out that the gray-crowned babblers are cooperative breeders. They have helpers at the nest, just like those scrub jays did. And in this case, the young males help at the nest. And these males are typically relatives to the parent, to the pair at the nest. They're offspring, typically. So they're helping raise siblings. Okay? And so here's what they decided to do. They decided to look at several groups, what they called, control groups and experimental groups. And in the control groups, none of the helpers were removed from these groups. So they were looking at the total number of offspring that were fledged from a nest over seasons, the number of offspring produced at a nest, in two conditions. Control groups would be, hey, they left them alone and there were helpers there, helping at the nest. The experimental groups, all helpers but one, were removed from these groups. So if you had 3 helpers, now you only have 1. We removed the other 2. And then we looked at the number of fledglings produced. And you can see that the number of fledglings produced by the control groups is about twice as many as from the experimental groups. What does that tell us? Well, it tells us that helping helps, that having helpers at the nest increases the number of offspring that survive at these nests. Does this show us that there should be selection for cooperation there should be selection for helping at the nest or cooperative breeding in these animals? I think I need to see more research to be convinced that helping at the nest increases the inclusive fitness of these young male helpers. What would I need to also study if I wanted to be sure that these helpers were doing the right thing, so to speak, in terms of their own fitness? we'd have to compare, we'd have to look at young males who decided not to help but tried to breed on their own. What were they doing? If they weren't helping, were they successful breeding on their own and raising their own fledglings? And how many fledglings could they raise if they were not helping but instead reproducing? That's really important. And Brown had to look at that as well. You have to look at what the costs are, so to speak. The cost of helping is not being able to reproduce on your own. And if you can reproduce on your own and raise a bunch of offspring, then it pays off to reproduce on your own and gain direct benefits, direct fitness benefits, than helping, right? So Brown did find that these young males were not successful reproducing on their own. And so helping was a way that they could increase their inclusive fitness rather than simply not being able to reproduce. But that would be important. Okay, I'm going to start this on the next video.